Okay, so welcome back, and in this video we're going to be looking at hydrogen NMR. In the previous videos we were looking at carbon NMR, and from a carbon NMR you can get two pieces of information. You can get the number of different environments that the carbons find themselves in, and by looking at the chemical shift it can tell you something about the type of environment that that carbon is in. Hydrogen NMR gives you a few more pieces of information about your molecule. It is a little bit more complex, but will give you more detail. Okay, so we're going to be looking at page 7 of your notes, and we're looking just at some molecules. Now the first thing we're going to look at is the number of different hydrogen environments. This is exactly the same as the carbons. So here, for example, we have two hydrogen environments. These two hydrogen environments on the end, the CH3 groups, are identical to each other, and then we have this CH2 group in the middle, which is a different hydrogen environment. Moving on to this example, each of these hydrogens is in a different environment. So we've got three hydrogens here in one environment. Now these are different from these three hydrogens. The reason that they are different is because these hydrogens are adjacent to this carbon here with a bromine on it. These hydrogens adjacent to the next carbon along the chain has got two hydrogens on it. So these two are not in the same environment. So here I have 1, 2, 3, 4 different environments. Again, another molecule here. This one's a little bit more complex. Again, I have all of my hydrogens in different environments. So I've got 1, 2, 3, 4, 5 hydrogen environments. These two CH2 groups will be very close, but they won't be identical because they're not in an identical environment. You have to look along the molecule. If you have an identical environment, then it will be one signal, but if they're different from each other, it will be two different signals. For example, in this one, these two hydrogen environments are equivalent because they're in the same environment. In other words, looking along the molecule, they see the same thing. They are different from this hydrogen environment as they look along the molecule. So the first example I'm going to do is methyl propene. So methyl propene is double bonded carbon, that's my propene, and then I have a methyl group on that second carbon. So I have a CH3 group here, and I have these hydrogens here. So in this case, I have two hydrogen environments. These hydrogens here, they are in the same environment. So that's one environment. And then these 6 hydrogens here on these two CH3 groups, they are again in the same environment. So that gives me two signals in my NMR. So what I'd like you to do now is to pause the video and have a go at the rest of them on that page. Okay, so that's page done out for you. So just going through them very quickly. Propene, where I've got 3 different hydrogen environments. That is 1, 2, 3 environments. The 2-chloropropane, these hydrogens on the ends of the molecules, they are in the same hydrogen environment. So that is just one environment. Again, here, propanone, all of these hydrogens are in the same environment. Doesn't have to be connected to a carbon. The hydrogens can be connected to a nitrogen or an oxygen. And here, methylamine, we have 2 environments. With things like esters, each of these hydrogens is in a separate environment. Some of them will be quite close and might even overlap, but they are 4 distinct signals. If I take something like 1,2-dibromopropane, I will have 1, 2, 3 different hydrogen environments. If I take this ester, dimethyl ethyl propanoates, we've got 2 signals here from these 2 hydrogen environments, but then if you look, these hydrogens here, all of these are in the same environment, so there will actually be 3 signals. Last but not least, if I look at but2-ene, these 2 hydrogens are in the same environment, and these hydrogens are in the same environment. So I'm going to get 2 peaks. So that's the first piece of information that hydrogen NMR gives us. So the number of signals in our hydrogen NMR chart equals the number of hydrogen environments. And that just gives us the first piece of information about our molecule. So the next piece of information we can get is the number of equivalent hydrogen atoms. And this is to do with the area under the curve. So this is not used in carbon NMR. This doesn't work for that one, but it does work with hydrogen. So it's the overall area that the signal covers, which gives us the ratio of hydrogens in the different environments. So this is quite often given as a relative intensity. So for example, 1.2 to 1.2 to 1.8 would turn into a 2 to 2 to 3 ratio. Now that doesn't mean I've got 2 hydrogens, 3 hydrogens. It could be 4, 4, 6, or so on. But I've got them in the ratio of 2 to 2 to 3. The other way of showing them is using this. This is what we call an integration trace, because we're measuring the area under the curve. And if we measure the height of these lines, I get 14 to 28 to 42. So that would be in a 1 to 2 to 3 ratio. Again, doesn't mean I've got that number of hydrogens. They could be 2, 4, 6, but they will be in that ratio. So we're on page 8 of your notes, and there are 4 charts for you to have a look at. And we've given you the integration traces, or we've given you the relative intensities. And you need to work out for me what the relative abundances of hydrogens in these different environments is. So there we've had a go at doing those. So dividing through by the smallest number, we get a 1 to 6 to 2 to 3 ratio. So that would be a 1, 6, 2, 3 ratio. Here we've got a 2 to 2 to 3 to 3 as the simplest whole number ratio. Here, by measuring the length of this integration trace, we get a 0.8 to a 2.4, so that will be a 1 to 3 ratio. Here I get a 1.2 to a 1.8, so that in whole numbers would be a 2 to 3 ratio. So that tells us the ratio of hydrogens in each of the different hydrogen environments. So that's the second piece of evidence that our hydrogen NMR gives us. We can look at the area under the curve, or the relative intensity, area under the curve, and that gives us the ratio of hydrogens in the different environments. So quite often we use solvents to dissolve our sample in a hydrogen NMR. We need to be quite careful of using our solvents, because obviously if they contained any hydrogen atoms, they could also appear in the spectrum and might hide the signals that we're actually interested in. So consequently we use solvents that either contain no hydrogen atoms at all, like CCl4, or we contain hydrogen atoms that have deuterium atoms, so the isotope of hydrogen, heavy hydrogen, which don't have any nuclear spin, because these would be H2 atoms, and you have to have an odd number of nucleons to appear in an NMR, and H2 obviously has an even number of nucleons. So to calibrate the spectrum, we use a small quantity of what we call TMS. This is tetramethylsilane. The reason we use this is it's got 12 hydrogen atoms. They're all in the same environment, so they're going to give me one clear signal. It's non-toxic, it's inert, it's easily removed, and it also tends to give us a signal further to the right than most signals. So most other signals are going to be to the left of this one, so we set this value to be 0. Now the next piece of information I can get from my hydrogen NMR is the same one that we got from our carbon NMR. In other words, we can look at the chemical shift. And the chemical shift values, just like they do in the carbon NMR, will give us an idea of the environment that the hydrogen finds itself in. As a general rule of thumb, the closer the hydrogen is to an electronegative oxygen, the more downfield shifted it is. So for example, in this case, this carbon here is attached to the C with the double bond O, so this will be slightly downfield shifted. These hydrogens here are attached to a carbon directly attached to an oxygen, so it's further downfield shifted, and these hydrogens here are furthest away from the oxygen, so they are the least downfield shifted. And this value here, 0, this is where I would see my signal for my TMS. So this gives us the last piece of evidence in this section, and this is the chemical shift. And just like in the carbon NMR, the chemical shift gives us some information about the type of environment that the hydrogen finds itself in. So we get 3 pieces of information from what we call a low resolution NMR. The number of signals gives us the number of hydrogen environments. The relative intensity, or the area under the curve, that gives us the ratio of the hydrogens in their different environments. And the chemical shift tells us something about the type of environment. So on the bottom of page 10, we've got 6 examples, and we'd like you to draw those out and have a go at doing them. Okay, so we're on page 11 of your notes, and we're looking at the first example we asked you to draw out, which was propanoic acid. And as you can see here, propanoic acid has 3 hydrogen environments, A, B, and C. The A environment is very downfield shifted. It's a high chemical shift value because it's a COOH hydrogen. The other 2 are CH3 and CH2, are B and are C, are alkane hydrogen environments, and they are much lower chemical shifts. So we've got there the 3 hydrogen environments. Don't worry about the moment about the fact that B and C look like they've got several lines attached to them. The reason for that is what we call coupling, and we're going to be studying that in the next video. The next one we're going to be looking at is 2-chloropropane, and as you can see there, it's got 2 hydrogen environments. You've got environment A, which is the peak at about 4.7, and you've got the peak B, which is the CH3 peak. Now the peak A, because it's directly attached to a chlorine, is slightly more downfield shifted than the 2 CH3 groups. But do notice the 2 CH3 groups are in the same environment, so you've got 2 peaks there. The next one I'm going to be looking at is propanal. So this has 3 hydrogen environments. Again, we have a very downfield shifted hydrogen, group A. So the hydrogen here, this is group A, and then we have B, and then we have C. So these are my 1, 2, 3 hydrogen environments. The hydrogen of an aldehyde functional group is very downfield shifted, so it's got a very high chemical shift. The next one we asked you to draw was 2-methyl-butane. Now it does have 4 hydrogen environments. You can see them there, A, B, C and D. However, because they are all alkane hydrogens, they're very close together. So the difference between B, D and C is 0.869 and D is 0.865. So they do tend to go on top of one another, which is why you can't see 4 clear, distinct signals. In the exam, we would either zoom in on the range 0 to 2.5, so you could see them in much more detail, or we would clean them up for you so they look a lot cleaner. But there are technically 4 different signals here. Notice the 2 CH3 groups on the end of the molecule, this end here, so these 2 CH3 groups are in the same environment, so these are both environment C. The next one we're going to be looking at is the ester methyl propanoate, and it has the 3 hydrogen environments you can see there, A, B and C. So the A environment is slightly downfield shifted because it's attached to the oxygen of an ester group, then the B and then the C. You'll notice I haven't included methyl propene in this, and that's because I couldn't find the spectra of methyl propene, but that was quite easy to work out. It's 2 hydrogen environments.